Let me tell you before we start, there are probably only really three things you need to really remember about probability throughout this course. And that is that probability is just simply the chance that something does or does not happen. So if I told you the probability of us having class tomorrow is 0, what does that mean about us having class tomorrow? We're definitely not having class. If I tell you that the probability that we will have class on Monday is 100%, what does that mean? We're definitely having class. If I tell you there is a 67.9% chance that I will have all your tests graded and your grade reports emailed out to you over the weekend, what does that mean?
Probably, but maybe not.
Probably, but maybe not, because there's always something that could happen. Okay? Those three facts are your basic understanding of probability. And as long as you keep that in mind and don't worry about memorizing a bunch of rules, think these things through, then probability will not beat you. Probability is not going to be that tough as long as you keep an open mind and are willing to actually think about things and think them through. So we will begin with some terminology. And the first terminology we have is, what is an event? In my example of having class, that would be an event. It's a collection of results results, or it's the outcomes of some kind of a procedure. It could also be, besides talking about the probability of having class, it could be the outcome of rolling a die, or flipping a coin, or reaching into a bag full of M&Ms and drawing out a blue M&M. Those are all probability types of events. A simple event is an outcome or event that can't be further broken down into simpler components. For example, if I was talking about the event rolling a die and tossing a coin, that would not be a simple event because there's two different steps to it. So rolling a die is a simple event and tossing a coin is a simple event, but it's more complex when you link them up together. The sample space consists of all the outcomes in a simple event. For example, in the event of coming to class, there's only two outcomes. Either we do or we don't. If you toss a coin, there's only two possible outcomes, heads or tails. If you talk about rolling a die, there's only 6 outcomes. 1, 2, 3, 4, 5, 6. If you're talking about drawing a card out of a well-shuffled deck, and what's the probability that you will draw the ace of hearts? That's 1 out of the 52 different cards, because there's 52 different cards you could draw, so that's 52 outcomes. And that would be the sample space. You'd have to list out all the cards. Okay? The notation that we'll use, P denotes the probability, and A, B, and C, and so forth, are events. They're always listed with capital letters. P parentheses A denotes the probability of event A actually happening. For example, if you flip a coin, what's the probability it will land on heads? 50%, or 1/2, because there's 2 outcomes, heads and tails, and heads is only one of those 2. So you would write that the event is H, the coin lands on heads, and you write it as P of H, and read it as P of H. So we say P of H, probability of getting a head, is 1/2, or 50%. You can express probabilities as fractions or decimals or percents. The fundamental counting principle basically helps us figure out how many ways compound events can occur. If an event can occur in M ways, and the second event can occur in N ways, then the number of ways the 2 events can occur together is M times N. For example, if I were going to flip the coin or roll the die, there's 2 outcomes on flipping the coin. heads and tails. There's 6 outcomes on rolling the die. 1, 2, 3, 4, 5, 6. So I could get a head and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, or a head and a 6. Or switching out the head for a tail, I could get tail and 1, tail and 2, tail and 3, tail and 4, tail and 5, or tail and 6. That's a total of 12 outcomes. The numbers 1, 2, 3, 4, 5, 6 will be paired with either heads, that makes 6 of them, or with tails, and that makes all 12.
And that's, M times N is assuming that order counts.
That gets into permutations and combinations. But yes, it does assume that order counts.
Because rolling two dice, a 1 and a 6, and a 6 and a 1 are two separate
Outcomes, that's right. That's right. So if you're rolling a pair of dice, it's 6 times 6, which would be 36 different outcomes. Because there's 36 different pairs of the numbers 1 through 6. If you have 2 of them.
But yet there's only 11 possible outcomes if you're counting the numbers.
If you're counting the sums, yes, there's only 11 outcomes. Actually, no, that's not true. There are actually 12 outcomes.
12 is the maximum. You can't have a 1.
You can have well, that's true. That's true. So it's 11 different outcomes. Okay. This is an example of fundamental counting principle. And hopefully, if it's going to work, it would be nice. For some, okay, it's turned out.
Offers apartments with 4 different options designated by A through D. Option A is the total number of bedrooms. You can have 1 bedroom, 2 bedrooms, or 3 bedrooms. We've got 3 choices here. Option B is the number of bathrooms. You can have 1 bathroom or 2 bathrooms. We have 2 options here. It can either be on the first floor or the second floor of the apartment complex. So there are 2 options. You can have a lake view apartment, a golf course view apartment, or no special view at all. And so there's 3 choices. According to the fundamental counting principle, how many apartment options are available?
Sorry. Well, why did it go off?
We'll find this by saying 3 times 2 times 2 times 3. All right, so I've got 3 times 2 is 6 times 2 times 3. And then 6 times 2 is 12 times 3 is 36. There are 36 different options available. One of those options would be a 1 bedroom, 1 bath, first floor lake view apartment, where I could have a 1 bedroom, 1 bath, second floor lake view apartment. There are a total of 36 different ways that I can combine my options. I'm just trying another example. Okay, example number 2. A car model comes in 9 colors, with or without air conditioning, with or without a sunroof, with or without automatic transmission, and with or without anti-lock brakes. And how many ways can a car be ordered with regard to these options? All right, so as far as colors, we have 9 colors. We have 2 choices for AC, either with or without. We have two choices for sunroof, either with or without. And we have two choices of transmission, either automatic or not. And we have two choices for the types of brakes, either anti-lock or non-anti-lock. In order to find the total number of ways that this car can be ordered as far as the options are concerned, we will multiply 9 times 2 times 2 times 2 times 2. Now, according to the order of operations, I can just work left to right. 18 times 2 times 2 times 2, 36 times 2 times 2, 72 times 2 is 144. So there are 144 different ways to order this car with the options that are available. Now, if you look at your patterns here, from experience that you've had in previous courses, you could write this as 9 times 2 to the 4th power. Exponents could occur first then. That would give me 9 times 16. And then 9 times 16, that's 54. 91 plus the 5 is 144. All right, let's try another example. How many?
Okay. That one doesn't go there, so let me look at my PowerPoint. Okay, so let's stop and do some examples from your handout.
This one, may I have a handout?
Excuse me?
May I have a handout, please? Oh.
My card. Okay, so on the fundamental counting principle, you have the definition there of what it is. Let's see if we can work the problem. How many rolls are possible rolling 2 dice? That sort of accidentally came up. Not if you're rolling 2. Fundamental counting principle says how many ways can the first one come up? And then how many ways can the second one turn out? It'd be 36 because it would be 6 times 6, okay? So if the baseball manager has 5 pitchers and 2 catchers, how many different pitcher-catcher combinations could he field?
10.
Now 5 times 2 is 10. Suppose you're packing, go on vacation, and you pack these items. You have a pair of black and a pair of tan pants. You have a red, a white, and a yellow shirt. And you have a white pair and a black pair of socks. How many different outfits could you come up with?
12.
Now that would be 2 times 3 times 3. Now, I believe it'll take more than 12.
Isn't there
last one
only
she
Oh
two
wait,
pairs
there's only
of
2 socks, sorry. So yes, you are right, it is 12. 2. I'm determined to make that 3 pairs of socks. So that's 12 different outfits. So how many different outfits would you have? You would, assuming you have access to laundry, of course, you would have 12.
1, because I don't like to have more than one.
You just wear the same thing every day. Okay. I'm going to show you an example of a tree diagram, and then I'm going to let you see a different example of one. This is the example that I'm going to use. This kind of helps you spell out what the different outcomes are. So the first choice is going to be pants. And those can only be black or tan. The second choice is going to be for a shirt. So if you chose black pants, you could choose the red shirt, you could choose the white shirt, or you could choose the yellow shirt. And same thing for the tan. You could choose a red shirt, you could choose a white shirt, or you could choose the yellow shirt. And then you have your two pairs of socks. So your socks are either white or black, white or black, white or black, white. All the way down. I didn't leave myself enough room to write all of these. Let's try to get a big piece of paper. So for your pants, black or tan. Now you can wear the black pants with a red shirt. You can wear the black pants with a white shirt. You can wear the black pants with a yellow shirt. You can do the same thing with the tan. Tan pants, red shirt. Tan pants, white shirt. Tan pants, yellow shirt. And then for each of those outfits, you still have two choices for your socks. White or black. And you're probably sitting there saying, well, why would anybody want to do this? Well, first of all, not everything is deciding what kind of clothes you're going to have to get up in the morning. But if you need, for some reason, for a probability problem, if you need for some reason to figure out exactly what the different outcomes all look like, you can use a tree diagram to figure that out. If you're looking to have a specific outcome, it'll allow you to count those specific outcomes if you can actually list them out. So what this represents, this first, let me get a highlighter, that'll make it a little clearer what I'm doing. This particular outfit would be black pants, red shirt, white socks. And the only way that this one would be any different is that it would be black pants, red shirt, black socks. So what you do is you follow the branches of the tree through all of the different options, and that helps you actually list them out. So the next option would be black pants, white shirt, white socks. Or black pants, white shirt, black socks. Or black pants, yellow shirt, white socks. Or black pants, yellow shirt, black socks. And then these actually are going to be exactly the same as these. The only difference is going to be that the black shirts or the black pants are going to be replaced by the tan pants. So this would be tan, red, white, tan, red, black, tan, white, white, tan, white, black, tan, yellow, white, tan, yellow, black. So this way we can see that there actually are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes. 2 times 3 times 2. Okay? Now, if I wanted to investigate the probability of what is the probability that someone chooses a pair of black pants with a yellow shirt and white socks, there's only one. And that probability would be 1 out of 12. But if I were to ask you, how many ways are there to create an outfit with black socks? 1, 2, 3, 4, 5, 6. So 6 out of 12, 50%. Okay? So it just helps you count the different outcomes if you need to actually be able to visualize the outcomes. So that's the purpose of a tree diagram.
What did you put, was that 12? What is those 2 words?
Outcomes. Or 12, you could call it 12 outfits because in this case it's 12 outfits. Okay? Okay. You flip a coin and then roll a die. Draw a tree diagram to show the different possible outcomes. How many outcomes can occur? And if you're on your iPad, you can actually draw this out. Come down here and get your pencil. You can do it with a computer too. And I think that's kind of a big dot, so I'm going to draw it down a little bit. So your coin could be heads or tails. Let's see. And then we would have 1, 2, 3, and so forth. So y'all finish yours. Let me see if you know how to make a tree diagram. It's okay, it doesn't have to be beautiful.
Oh, it's not going to be.
Doing it with a mouse is harder than actually just doing it with your finger.
Did I send this in?
Yeah, you just click submit when you're done with it. And then as you click submit, I'll see your submissions on my screen. See, I'm not any better at it than you all are, so it's okay. Here's a good one.
We can't go ours anymore because this one's.
Oh, that's okay, I'll take it back off.
Oh, okay.
So let me close that one and let y'all continue. It's
They haven't taken this off yet.
Oh. I'm not sure what I did now. Okay, it should be back to you now.
Yeah, I didn't get to finish mine, but it's.
Mine says thank you. I'll have to start over.
Let me back it up. Does that take you back?
Yeah, start over.
Yeah, it's okay.
Okay, that's all right, just put something on there, because everybody does seem to know what's going on, because I can walk around and see you doing it. The reason I showed you the diagram was because I wanted you to have the experience of actually trying to draw. There's the very creative.
Yeah, it looks crazy.
That's right. That's a good way to do it. Let you get finished and then I'll,
Okay, yeah.
And then you want us to put all of the outcomes too?
you don't.
Yeah, I did do that.
It was the major thing was understanding the tree diagram.
Okay.
Now, you can also type on this. You just have to have all those turned off. So you can actually enter your text right there. So it's up to you which way you do it. I think everybody's turned one in now. And I see some really good examples. a nice one. A nice illustration. Whoops, yeah. Why is it not showing you? I didn't share it. We've got nice colors. And here's a good one. Because that actually gives you the outcomes in a nice, clean form. That's another good one. So y'all did well. So tree diagram is a picture of the possible outcomes of the procedures shown as line segments branching out from one starting point, and tree diagrams are sometimes helpful in determining the number of possible outcomes in a sample space if the number of possibilities isn't too large. We only had 12 possibilities, so this wouldn't be very hard. If we had done a tree diagram for the car problem where they were talking about 9 different colors and with or without brakes, and there were 144 different possibilities, we need a sheet of computer paper to be able to do that. In fact, you might need 2 or 3 sheets of computer paper taped together. It will be very hard. So the tree diagram is only helpful on small things. So let's see, we're not ready for that one yet. We've already done the examples on the worksheet. Are you ready to take a quiz? Okay. Click go. This one you're going to have to think through a little bit. And you do not have to draw a tree diagram. I'm not going to ask you what the different outcomes are. I'm waiting to see that screen for everybody.
Supposed to be the second question.
First one and the second one. If you're getting answers that surprise you, you're probably right. If you think your answer's too large, you're probably right. Because the fundamental counting principle is not at all intuitive. Sorry. I want to be sure everybody had a chance to submit before I go on. It looks like everybody's done, or mostly done. So we talk about the law of large numbers. But before we do, I will let you see the correct answers to the quiz. It's not working. We'll just go back there. Okay. So the access code for a car security system consists of 4 digits. The first digit can't be a 1. How many digits are there?
10.
There's 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The first digit can't be a 1, and the last digit must be even. So, and it was 4 numbers, right? So you have some possibilities for the first one, some possibilities for the second one, some possibilities for the third one, and some possibilities for the fourth one. For the first one, it can't be a 1. So though there were 10 digits, minus not being able to do the 1 is a 9. Then you have 10 choices for the second one because there's no restriction on that one. 10 choices for the third one, but only half of the digits are even. So that would be 5. Okay? So 9 times 10 times 10 times 5. And I'm going to use the calculator to do that. I don't trust my arithmetic ability quite that much. And I got 4,500. So there's 4,500 codes possible. And then the next one says they're doing license plates. The license plates are 3 digits and 3 letters. The digits can repeat, but the first one can't be a 0 or a 6. The letters cannot repeat. How many license plates are available? Okay, these are digits. This one can't be a 0, and it can't be a 6. So that only leaves how many? 8? And did it say all of them couldn't be 0 or 6, or only the first one? Just the first one. So we can use all the digits for the second one, and all the digits for the third
Wait
one.
a minute, all the digits would be 10.
Oh, yes, sorry.
It said not use 0. Then
Yeah, no 0, no.
It said no 0.
No 0 and no 6 for
First,
the first one.
First, but after that he took.
After that, you can use them all. And I messed up, put 9, there's actually 10. How many letters are there?
26.
26. Can the letters repeat?
No,
So how many letters do I have after I've chosen one of the first?
25.
You only have 25.
And 20.
And then 24. So this is going to be a very large answer, I think. We'll get the calculator. 8 times 10 times 10 times 26 times 25 times 24. A whole bunch are possible.
Yeah, you got it right.
So this is my answers. You can see yours now. Okay? You should be able to scroll down and see your responses and whether they were right or wrong. Okay? Now let's talk about the law of large numbers. And that problem, by the way, was one on your notes. The law of large numbers in the long run, as a sample increases, the relative frequencies of the outcome get closer and closer and closer to the theoretical or practical classical probability value. For example, if you flip a coin 20 times, you would think you would get 10 heads and 10 tails, ideally. But the chances are it won't always be exactly 10 and 10. If you flip it 20 times, you might get 8 out of 20 and you would only have 40%. But if you increase the sample size, the outcome of actually getting heads will get closer and closer and closer to the classical probability, which is 1/2. Okay? We're going to look at the probability applet. Well, I hope we would. It worked last night on it. Versus. Okay, I think it's on. That's why it wouldn't work. So, this is the applet, and we're going to go to a different page. So we're going to use this one. So let me go to the last page so you can actually click yours. And it's the one that says probability. It's about halfway down. Everybody find it? What you can do here is we're going to toss a coin. Now yours aren't going to look like mine. Mine will be different from yours. But the probability of heads ideally would be 0.5, and I can have it just go ahead and toss that many times, or I can tell it that I want it to toss it 200 times. So what I want to do is I'm going to start off and have you toss it 10 times. Tossed too many times. Let me try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got the actual probability that I should have. Did you?
Yeah, yours says 10.
It doesn't seem to be wanting to open.
It wouldn't open mine either.
On your iPad? I may have to look into it and see why it won't. You can look on with somebody next to you if your iPad's not working. Okay?
Change the number of tosses.
You can change the number of tosses by sliding to however many you want. And it will toss it that many times for you automatically. So I'm going to reset it, and I'm going to first have it to toss, again, 10 times. And we got 7 out of 10 heads and 3 out of 10 tails. We were expecting 5 and 5, but we didn't get that. If we toss it 25 times, and I'll reset it before I do the 25. What you see in that bar across the top of it is that it's shifting back and forth between the percentage of heads and the percentage of tails. So when I tossed it 25 times, I got pretty close. The probability of heads and tails was 48% and 52%, so it's much closer. But if I do the exact same thing again, it doesn't mean I'm going to get the same outcome. Well, I did for some reason. But that is possible. So here we have 50 times.
Head 89.
And notice what's happening here is it's straightening out until the probability is in the middle at 0.5. This time we got 52% heads and 48% tails. So now we'll go 100. And again, we got 46 and 54%. Okay? And the highest will go, I think it's 200. And again, we got pretty close, 0.415 and 0.585. So if I only tossed it 5 times, or actually if I only toss it 2 times, I don't get very good results. But if I toss it 5 times, my results improve just a little bit. So it's only with large numbers of tosses that they actually get really, really good. And the larger the number of tosses, the better you get. That's the point. So if we go back to Nearpod, we can talk some more about probability. You always express a probability as a fraction or a decimal number between 0 and 1. Why is that? Can you have a negative probability? No. Can you have a probability that's more than 100%? No. Now, people say you have to give 110%. Well, guess what? You can't give 110%. You don't have 110%. You've only got 100%. These are potential quiz questions. You might want to make a note of them. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. And for any event A, the probability of A is between 0 and 1 inclusive. The closer it is to 1, the more likely it is. The closer to 0 it is, obviously, then the less likely it is. We also need to talk about something called a complementary event. And this doesn't mean that it's going to pay you a compliment and say nice things to you. Complementary event is you might think of it as the absence or the opposite of the event. So if I toss a coin and I'm expecting to see a head, the complement of heads is a tail. If I have more than one outcome, the complement becomes a little tougher. If I were rolling a die and I was wanting to get an even outcome, then the complement of that would be the odd numbers. Or if I was rolling a die and I wanted to get a 5 or a 2, the complement of that would be everything except 5 and 2, which would be 1, 3, 4, and 6. So we'll do some examples now of the complement of an event. Oops, got a little carried away there. Suppose you roll one die. Find the probability that the die will not land on 3.
One out of 6.
Well, the probability that it will land on a 3 is 1 over 6.
Oh, well,
5 over 6.
It would be 5 over 6. And this line over the top of it is not 3. Some other ways you may see this if you do any, look like for YouTube or some other places that you want to get some extra instruction. This might also be written as probability of 3's complement. Find the indicated complement. A recent survey shows that 64% of all third graders bring their lunch to school every day. What would the complement of that be? Be 36% of all third graders do not bring their lunch to school every day. Okay, either they bring it or they don't. Odds, if you do any gambling, odds is a comparison on the probability of an event to the probability of its complement. So you have the probability in favor of an event, you put the probability of the event on top, and the probability of its complement on the bottom. But if you have the odds against an event, then it's the probability of the event not happening divided by the probability that it does. So for example here, suppose there's 12 boys and 10 girls in the classroom. First, let's find the probability of choosing a girl. How many girls are there?
10 out of 22 total.
Okay. What are the odds of choosing a girl? Now, this is the probability that we did choose a girl. The probability that we didn't choose a girl
12 over 22.
is going to be 12 over 22. So going to the odds in favor of is we take this probability and divide it by this probability. And if you remember your fractional arithmetic, that's 10 over 22 times 22 over 12 because you flip and multiply. The 22s will cancel and it turns out to be 10 over 12 or 5 over 6. And we usually write that as the odds of choosing a girl are 5 to 6. We read it top down. Oh, sorry. Yell at me when I do that. Find the odds of choosing a boy. Well, we could go back and refigure these probabilities, but the truth of the matter is, this is the probability of choosing a boy because it's not a girl. So if we want the odds in favor of choosing a boy, the probability of a boy is 12 over 22. And the probability of not choosing a boy is the probability of a girl. That's 10 over 22. So that turns out to be 12 over 22 times 22 over 10. That cancels. And you have the odds are 12 to 10, or 6 to 5. Okay? I'm going to have a little bonus assignment for you. I will bring it next time. But how many people have ever bought a lottery ticket? Why? Why?
Turned
Had the
18.
feeling too.
The chance.
Yeah, it's a chance. Somebody's got to win, right? Well, somebody does eventually win.
After you've lost so much more money that you put into it.
Yes,
you
that's
get
true.
that percent.
The probability, I'll show you the one I have is for lotto. For the one that we do around here, I'll show you the odds of it. But I'll give you an analogy that I think you can really relate to. If you buy a lottery ticket, your chances of winning the lottery are larger than your chances of being struck by lightning twice in the same field during a single thunderstorm. You're more likely to be killed by lightning and struck again than you are to win the lottery with a single lottery ticket.
Aren't you not very likely to even die by a lightning strike anyway?
You're not unless you're standing out in the middle of the field in a thunderstorm. Then you might.
That's true.
Okay?
Well, see, this is a problem with probabilities and statistics. It's because you tend to think of them as actually meaning something. For example, what's the probability of somebody driving along the interstate and a piano falling out of a 747 and squashing?
Not very high.
Pretty low,
Pretty low.
but for the
Not-
guy
but it's not zero.
for the guy on whom the piano lands, it
It's
was
a big
100%.
deal. Yeah.
And for everybody else, it was 0. So,
Well, his is not necessarily 100%. He had the same probability of it happening to him as anybody else. But once it happens to him, he just,
well, the probability apparently was 1 for him to get.
it seems that way, but just because the event does happen to you, that's the probability after it happens. But as he's driving along, he has the same probability everybody else does.
Yeah, but if he's the one that gets squashed, the probabilities didn't matter too much.
Well, no, the probabilities didn't matter to him at all because he got squashed. I'll agree with you there. Okay. Let's see where I am. Okay, I think is the next one like this? I took mine apart and I've got my pages mixed up.
That's like the next after page of that. There's a page in between that.
Okay, so it's,
It's only like 40
This one. oh, okay, here I found it. Okay. Trying to see where I was on the beer pot. Suppose there's 4 yellow, 3 pink, or excuse me, 5 pink, 3 blue, and 7 white beads in a bag. Find the probability of drawing a blue bead. First of all, how many beads are in the bag?
19.
Okay. So there's 19 in the bag. And 3 of them are blue. So it would be 3 over 19, or if you prefer decimals and percents, it would be 15.8%. Always round up a fraction of a percent. So you can give it as a decimal. Most of us understand percentages better than we do the decimals. What are the odds in favor of drawing a blue bead? Okay, this is the probability you draw a blue bead. And the probability you don't draw a blue bead. Would be 16 over 19. So if we divide those two, remembering once again it's 3 over 19 times 19 over 16. And the 19's canceled. Whoops, I'm behind my calculator. I'm getting off of there. Then the odds are going to be 3 to 16. Now at this point, does anybody see a much shorter way to figure these out? Do you really need to do this fraction arithmetic? What always cancels out? Yeah, your total always cancels out. So you want basically the number of boys out of the number of not getting boys. So find the odds against drawing a pink bead.
14 over 19.
Okay. So that will be 14 to 5,
Yes.
or 14. Now this is the odds.
That's you taking out pink totally, like
Yeah.
not having the option.
Right. And then find the probability of drawing a bead that's not white. Well, 7 white ones.
It's 12 over 19.
There's 7 white beads in the bag and 19 total, so that's going to be 12 over the total in the bag is 19. Find the odds in favor of drawing a white or a blue bead.
So when it says or, do you add them?
Because white beads are white and blue beads are white or blue. So you count them all. So let's see, we have 7 white, 3 blue, which
10.
makes 10 that we have. And then how many of them are not white or blue? So 10 to 9. Okay? What's the probability of drawing a yellow bead? See, there's 4 yellow beads and a total of 19. Would be 21.1%. Are we good with that? This makes sense?
Yes.
Can you
Yes,
do,
Kristen.
The odds against drawing pink bead one more time?
The odds of drawing the pink bead
Against.
drawing the pink bead. Okay. Let me go into a little more detail on it. Okay, the probability against what goes on top? Look at your formula if you need to. Hmm? Well, look on your Nearpod screen. Odds against are the probability that it's not the event, so not pink, over the probability that it is pink. So the not pink beads, there are how many? $14. Because there's a total of 19 beads, and 5 of them are pink. Okay? How many beads are there that are pink? Well, we don't usually write it as a fraction, and we give the odds as the numerator to the denominator. And the gambling jargon for that is that you have better than even odds. Even odds means 50-50. So this one means you're more likely to get a not pink bead than you are to get a pink bead, because there's 14 ways to get it if it's not pink, and only 5 pink ones. Okay, so that's better than even odds. And then if you go back up here to 3 to 16 for the blue ones, for the odds in favor, that's less than even odds. Okay, now we need to define something new. And I'm going to come back to the quiz in a second. Go ahead and finish off this page. A compound event is any event that combines 2 simple events. As I said, tossing a coin, rolling a die would be an example of a compound event. Two events are disjoint if they do not occur at the same time. Okay? If you have event A that you randomly select a person that is a female student, and event B is that you randomly select a person that is full-time or works full-time, and then random event C is that you randomly select someone who is unemployed, not employed at all. Are events A and B disjoint? The question you ask yourself are, can a female student also be working full-time? What's the answer to that?
Yes.
Yes. Therefore, they are not mutually exclusive. Are events B and C disjoint? Can someone work full-time and also be unemployed? No. So unemployed means they don't work.
Can a cat be alive and dead at the same time?
If it's struggling with a cat, it can be. Think about these two events. Event 1 is that you roll a die and you get a 2. Event A. Event B is that you roll a 5. Are those events mutually exclusive? Yes, because you can't roll a die and get both a 5 and a 2 on a single row. So those are mutually exclusive. What's the probability that you roll a 2 or a 5? How many outcomes are favorable to what you're asking for? There's actually 2. If you roll a 2, you succeeded. If you roll a 5, you succeeded. So the probability of 2 or 5 is 2 out of 6, or 1/3. Does that make sense to everybody now? Because you can't roll a 2 and a 5 on the same roll. There's 2 different possibilities for you to succeed in what you're trying to get. And there's 6 different outcomes. Okay?
Can you leave that there for just a second?
Sure. I'm still trying to figure out which page is next. Is it the table or the snowman?
Additional for any event.
And then it's the
And then it's a snowman.
Got that one. Are you done with your notes?
Yes, ma'am.
Okay. Okay, this is the addition rule for any events. It's on your Nearpod presentation. Suppose the YMCA has an enrollment of 4,563 people. Of these, 852 play in the basketball league, and 3,041 are men. Of the members of the basketball league, 520 of those are men. Are the events selecting a male and selecting a member of the basketball league mutually exclusive or disjoint? By what you've been told up here, can a man be playing on the basketball league? Yes. So are they mutually exclusive? No. If you select YMCA members at random, find the probability that a selected person is either male or in the basketball league? How many men do we have total?
520.
Well, it says in the basketball league, we have 520. We have 3,041 total men in the YMCA, okay?
Read the question.
And how many do we have playing basketball in the league?
520.
No, that's just the men. There's a total of how many in the league?
852.
852. Is there any crossover between these people that I'm counting? How many are in the crossover?
520.
That's 520. We can't count that 520 men as both men and as playing in the basketball league. They don't get to vote twice. Okay? So you have to take out the overlap. And then we have a total of 4,563 people at the YMCA. And now I'll use my calculator to make sure I don't add wrong. So I have 3041 plus 852 minus the 520 men. And then divide that by the total number of people at the YMCA, which is 4,563. And there is a 73.9% chance of selecting a person that is male or in the basketball league. Does anybody have any questions on that one? Because that's one of the ones, even though I put the rule up for you on your Nearpod, really if you think through it, it makes more sense. Or at least I hope it does. Okay? The next thing that we'll talk about is a quiz. Get mine back up here. So let's answer some questions. Let's see if everybody's getting this right. So everybody's still working? Because I can't always tell from looking at mine. So you should be able to see the correct answers now. Okay? Apparently, question 3 was kind of challenging for everybody else, was question 4, so let's look at those. Math department at a community college has 7 male professors, 7 female professors, 11 male teaching assistants, 10 female teaching assistants. A is that you select a male, B is you select a professor. Are A and B disjoined? Can a male be a professor? Yes. So are they disjoined? No. Okay? Same setup. What is the probability you select a male or a professor out of the department? Well, we have 7 male professors. We have 11 male teaching assistants. That makes 18. And we have a total of 18 males, but can we count all of them? Are these different from these males?
Yeah.
Yeah. So 7 plus 11 is 18. But then it says, or a professor. Well, can we count the male professors twice? No. So we only add the male professors and the male teaching assistants together, and that's why we get 25 over 35, because 7 plus 7 is 14, 24, 25, 35 total teaching positions. Oh wait, I'm sorry, I forgot to include them. These women professors will be very upset with me. Okay, so we have 18 men and then an additional 7 female professors, and that's why it's 25, not just 18. Sorry, I was only counting the men. That wasn't nice.
We won't tell anybody.
Okay. Okay, we will, let's see. No, we've got time to do a little bit more. Let me go back while we're assessing how well everything is. I want you to give an example of a disjoint or mutually exclusive event that you haven't already talked about. Tell me two things that are mutually exclusive or disjoint. And you can type your answer on this one. I have to share an answer with you.
It's submitted by answer, but I only put one. Is that okay?
Oh, I can go back. I can do that. Let's see. That should let you back in. Some of these are very good. about another minute. Okay, let me share some of the answers. Pick a child in the population younger than 18, or an adult in the population 18 or older. You're not going to have anybody that falls right on the edge. They're either younger than 18 or 18 or older. This is a good one. Event A is a student getting grade averages in A, and event B, the student doesn't attend class. King cards when you're playing cards, and aces when you're playing cards. Kings and aces are not the same thing. They don't overlap. This one's a good one too. A is the men in the NBA, and B is the cheerleaders in the NBA. The cheerleaders can't play in the game while the men are, and that's why they're cheerleaders. Event A, going to Taco Bell. Event B, ordering a hamburger. Not order one at Taco Bell, but you aren't going to get one. So it looks to me like y'all have got a pretty good understanding of that concept. Okay, I think we will, since it is 1:23 and we're supposed to, we didn't take a break today, I think we will wrap this up for the time being. And we will pick back up on the notes pages, the bottom half of that page, and then this last page. I'm gonna take it up at midterm. I'm gonna take your Happyville projects up at midterm. At that point, you should have the first 5 of them done, and then I'll take them up again at the end of the semester. Okay? Everybody have a good day. If you haven't done